So, under process capability analysis, now I am going to discuss one important topic called setting tolerances and specifications for components and assemblies. And there are three issues involved over here, like how to set the tolerances on assemblies. That is the first issue. We are going to discuss this. The second important issue is how to set tolerances on individual components. Assembly consists of a number of components. So here given the assemblies, the tolerances, how to set the tolerances of the individual components. And the last important topic in this context we are going to discuss, that is that how to set tolerances on the mating parts. Is it okay? So this will be our discussion topics. And the first, let us talk about the first issue, that is setting tolerances and specifications for assemblies and components. Now you are dealing with different kinds of products. So usually for from a repetitive manufacturing systems, or from say a batch production systems, so the kind of product we get, this any product is nothing but an assembly. Assembly of what? Assembly of different types of components, and or the different kinds of sub assemblies, or the components and sub assemblies, and they are assembled as per the product structure code. That means whenever you design a product, so you develop the bill of material. So what is this bill of material? Bill of material is basically a document which says, or which mentions that how many different types of the parts and sub assembly you require to produce one unit of the product. So that is the bill of material. Now this bill of material, this document can be made in terms of the hierarchy. Okay, that means from the assembly level, so then you go to the, move to sub assembly levels, sub assemblies to sub assemblies, and ultimately you reach down the line to the component level. So this sort of the structure is referred to as the product structure code. Now this product structure code must be known before you go for assembly work, and you also must know what is the configuration. So the two important aspects must be known related to product design. One is your product structure code, and the second one is the configuration. Now, tolerances of quality characteristics of the assembly. Now what you need to do, that means suppose you get the assembly. So the assembly, when you look at the assembly and the product, you may find you can identify several, say, quality characteristics of the final product. So you just pick up one, and then you relate this quality characteristic to the component quality characteristics, whether the final assembly quality characteristic, and is in which way this quality characteristic is related to the individual component quality characteristics. So this relationship must be known, and only when you have the information related to the configuration of the assembly, you may be able to relate the final the assembly quality characteristics with the individual component quality characteristics. Okay. So similarly, so the tolerances of the quality characteristics of the assembly obviously are dependent on the both individual component tolerances as well as the configuration. Is it okay? If the configuration changes, the relationship may change. Is it okay? Now the next important point to be noted, that is the tolerances of the assembly are to be assured such that the process making the assemblies or the components are capable. You know what is, you know under what condition we say that the process is capable. So the first condition is, as far as possible, the process must be made centered of the process, centering of the process. That conditions you have to achieve. And the next thing what you have to do, that means you make sure that the value of CP, process capability ratio, okay, is at least 1. Now these assumptions we will make, and based on these assumptions we will determine the relationship between the component tolerances and the final assembly tolerance. This will ensure high proportion of conforming output. That means we say that if we say that the CP, process is centered, and CP is 1, that means we are concluding that the process is highly capable. That means there will be hardly any non-conforming units you find from the process. Is it okay? So that condition is to be ensured. Now let us talk about the tolerances on assembly. How do you determine the tolerances on the assemblies? How this the assembly tolerance is dependent on individual component tolerance. So assemblies are made with components joined together as per a given configuration. Now how do you join? There could be many kinds of the joining technology, like say welding, and we assume that the weld quality is very good, so that the weld strength is acceptable to you, and the length of the weld length, is it okay, between say the two parts getting joined, this weld length is very small, and that's why it can be negligible. So these are the assumptions we will make. Now there could be several examples. Examples are plenty. So like I am just mentioning 2 simple examples. One example is this: you have this configuration. That means the final assembly, it consists of 4 parts, okay, A, B, C and D, right, and these parts are joined, means these are the weld joints, and we are assuming that these 3 weld joints, okay, the weld length, the weld width is negligible. Is it okay? Now obviously these the components, they are produced in large numbers, and so the component the dimension is x1, component A dimension. Similarly, component B dimension is x2. For C it is x3, and for D it is x4. And all these components, they are being produced in large numbers. Obviously, these x1, x2, x3 and x4, these are all random variables. Is it okay? Now, when you get the final assembly, you have this shape, and now you have to identify that what is the most critical quality characteristics of the final assembly. So supposing the most critical quality characteristics is y. So how do you relate y with individual x values? Obviously y is x1 plus x2 plus x3 plus x4. Simple example. Now let us move to the second example, example 2. That means in this assembly what you have 3 parts, and part A, part B and part C. So what you have, that that this is the configuration. So as per the configuration, what you do, that means you weld part B with part A, and similarly you weld part C with part A. Now you get this assembly, this is the shape. Now what is the critical quality of the final assembly? You say y. What is this y? That means this is the exposed area or exposed length. So suppose the exposed length is the critical quality characteristics of the final assembly. Now this is that means how this exposed length is related to the individual x values. That means related to A, the random variable is x1, related to B, x2, and similarly related to C component C, you have the random variable x3. So how do you relate y, that exposed length, with the individual the random variables? That means y is x1 minus x2 minus x3. So once the configuration is known, so you have probably understood that while you deal with an assembly, the basic the relationship will be known only when the configuration is known. If the configuration is not known, you cannot have you do not know the relationship between the final assembly quality characteristics and individual component quality characteristics. So that is the first the conditions we have arrived at. Next is so in general what you find that y is basically, suppose the y is the final assembly as a quality characteristic of interest. So you may assume it to be linear combination of individual component dimensions. So these xi's are basically individual component dimensions. So it's a linear combination. That means you say that A1 x1, A1 is the weightage, plus A2 x2, that means related to second dimension, the weightage is A2. And similarly, if you have k number of components, is it okay? For the kth component, the corresponding weightage is ak. So it is sigma I equals to 1 to k ai xi. So it's a linear combination. This is a general form. Now, obviously, as I have mentioned, that all these individual dimensions xi's are assumed to be a random variable, because you are getting several values. It's not that just one unit you are producing or one assembly unit you are producing. You are producing multiple units, and multiple units in the sense the large numbers is a running production system. So that sort of many a time we may assume it to be a mass production system. So it's large number. So under certain these conditions, xi is a random variable. That means individual dimensions. And if it is a random variable, so you can you know what is its mean. So the mean notation is mu I, and standard deviation SD stands for the standard deviation, that is sigma I. Is it okay? So this information you must have at any point in time. Is it okay? So what we need to do when these individual dimensions are assumed to be a random variable with their mean and standard deviation values known, and they are all estimated, then you need to know that related to the final assembly quality characteristics, that is y, relevant quality characteristics, what could be the expressions for the final assembly quality characteristics mean, and similarly the final assembly quality characteristics standard deviation. So what are these notations? That is mu y and sigma y. Okay. So how do you relate mu y with individual mu i's, and how do you relate sigma y with individual sigma i's? So that is the questions. So for example, you refer to example 1, that is the 4 components we consider, and the 4 components are joined, and you get one assembly. So if you refer to example 1, so obviously mu y is equals to mu 1 plus mu 2 plus mu 3 plus mu 4. Is it okay? That means what is that equation? That means the sigma I equals to 1 to k mu I, ai mu y. Is it okay? So ai mu y. So what is ai over here? Here all these ai values will be 1. So that's why it is 1 into mu 1 plus 1 into mu 2 plus 1 into mu 3 equal weightage plus 1 into mu 4. Only 4 components you have considered. Is it okay? So in general we consider k number of components. For example 2, obviously it is mu 1 mu y is equals to mu 1 minus mu 2 minus mu 3. That means for the first component the weightage is 1, for the second component and weightage is minus 1, and for the third component weightage is -1 again. Is it okay? As far as the variance of y is concerned, the notation is sigma y square. So you have this generalization. That means ai square. What is ai? Ai is the corresponding weightage, we assume, ai square variance of xi. Is it okay? So what is the notation of variance of xi? That is sigma I square, because the standard deviation is sigma I. So it is sigma I equals to 1 to k ai square into sigma I. Is it okay? So for both the cases, that means for example 1, what is the variance of y? That is sigma y square. Is obviously you add them, the individual variances, that is sigma 1 square plus sigma 2 square plus sigma 3 square plus sigma 4 square. Is it okay? And similarly for example 2, the variance is given by sigma 1 square plus sigma 2 square plus sigma 3 square, because it is a square term. Is it okay? So the weightage is -1, but -1 square is 1. Is it okay? That's why it is plus sigma 2 square and plus sigma 3 square. Is it okay? I think the logic is very clear to you. Now once you have these values, that means the sigma y is known as well as mu y is known. So the remaining steps are very simple to understand. So what you try to do, you try to determine the natural tolerance limit. Just remember one very vital point, that whenever we refer to a particular process and we try to conclude about the process mean or the process standard deviation, so the corresponding the tolerance limits are referred to as the natural tolerance limit. Is it okay? Natural tolerance limits. We add the term called natural because actually you have the design specifications, but to what extent design specification is actually your target. Now when you get a process to achieve this target, now the process condition is varying, and you are affected with many types of factors. But what you have mentioned, that at least I have made the process controllable. That means the process is in statistical control. That means the process is affected by the natural causes. That means if you refer to different kinds of patterns we have discussed, that means it's a natural pattern. So that's why the natural the term may come, and that's why these tolerance limits, which are actually which you get, these are referred to as the natural tolerance limit. I think the logic is made very clear. So why it is referred to as the natural tolerance limits. So how do you determine the natural tolerance limits for the y? That is the critical quality characteristics of the final assembly, assuming normal distributions. Again, that is the basis in fact. So right now we are discussing the situations where the normality assumption holds. If suppose due to some reasons, supposing you are dealing with less number of units, many cases, is it okay? Like say the production lot size is very less, unique one. So obviously the normality assumption may not hold. Is it okay? But those are very special cases. Right now we are we are referring to a manufacturing system which is referred to as the batch production, repetitive manufacturing. And in any country you will find that as far as manufacturing system is concerned, 70 to 80% of the products which you use, which you get, which you manufacture, they come from a batch production system. So our focus is on the batch production systems, and so in majority of the cases the normality assumption holds. If you deal with the data, you will come to these conclusions. So what is the natural tolerance limit? Obviously mu y plus minus 3 times sigma y. So once this is known, next one is, so the next important issue, that is the tolerances on components. That means now what you try to do, that means in the previous case the individual tolerances are known. You are determining the tolerances of the final assembly. Here the case is just the reverse. Here assembly tolerances Okay, assembly related quality characteristic is known, corresponding tolerances are specified. Now you know the configuration of the assembly. What you need to do, you need to determine the tolerances of the individual components, and once you determine these tolerances, then you check that whether these tolerances are acceptable to you or not. That means why do you say it is acceptable? Because if those tolerances you can produce, that means you have the corresponding process capability. So like we say, that ability to produce as per the specifications, as per the tolerances. So basically, suppose you find that the individual tolerances are not acceptable. Okay, it's possible. You cannot relax the tolerances of the final assembly, because ultimately the product will be known by its assembly, but the assembly quality characteristics. So what you need to do, that means at the component level, you must look into the design aspects, the design improvement aspects. So just all these points I have elaborated here. Let me read it out. Here the problem is to determine the tolerances of the individual components when the tolerances of the assembly related quality characteristic of interest are pre-specified. This point I have mentioned, the pre-specified, it's already known, and the processes are capable, that means Cp is equals to 0, Cp is equals to 1.0. So with the process centered. This is all we have been saying, that the process is to be made centered, and then make sure that the process is capable. That means the value of Cp must be at least 1. If the individual component tolerances are not met, that's the point I have already highlighted, we refer this problem to the design team after getting the data and information pertaining to the present capability of the process. That must be known. Whether to what extent, the tolerances, individual components tolerances, which are not acceptable to you, to what extent they affect the process capability, okay, corresponding to that particular say the component. So each component, whenever you identify each component, you are also in a position to identify the corresponding processes. So individual component tolerances can be estimated when the variances of the individual component dimensions are known. Is it okay? So the same exercise we do, and we'll take off numerical problems, and then you will come to know that how the process has been reversed, and how to determine the individual component tolerances, and how to decide on their acceptability. Now the third important aspects we are going to discuss, and this aspect or these conditions frequently you encounter. That is how to set tolerances on the mating parts. You must be aware of for different kinds, for producing different kinds of assemblies, we need to use the mating parts. So what are these mating parts? Like say a shaft and the bearing. So that is one kind of assembly. So they are all mating parts. Similarly, a piston and a cylinder, another example of mating parts for creating assembly. Then a pin and a sleeve. So there are many such examples, in fact. Okay, so whenever you get such an assembly, you need say the mating parts, and the parts are referred to as the mating parts for these kinds of assemblies. This is a special kinds of assembly, and these types of assemblies you frequently you use and you design. Types of fit. Now here what is important is that between the mating parts, when you get the assembly, what kind of fit you may have. Now there are three types of fits you may be knowing, and these the fits are clearance fit, interference fit, and the transition fit. So that means the type of fit between the mating parts can be grouped under three categories. So what is a clearance fit? That means the size of the hole dimension is greater than the size of the shaft. So prior to assembly, so this condition, that means you create hole, you create shaft, and make sure that this condition holds. That means size of hole greater than size of the shaft prior to assembly. For example, a piston within a cylinder. Interference fit is just the opposite. Size of the hole is less than size of the shaft. That means you have to press fit, okay. Prior to assembly, these conditions you have to ensure. And a pin forced into a sleeve. There are many such examples, in fact. So it will be better as a student, as a learner, you identify those assemblies where the mating parts are used. Is it okay? So when you will carry out the exercises, we will be referring to many such examples, in fact. And then you have the transition fit. That means you are unsure whether in some cases you have a production systems, okay, you are creating the mating parts, you are going for the assemblies. Now due to many reasons, sometimes you produce a clearance fit, sometimes you also produce the interference fit. So it's either clearance or interference in the assembly. Is it okay? So in such cases you will find that the majority of the components, a substantial proportion of the assemblies may be considered rejected. So here is a clearance fit, okay, it is very clearly mentioned. This is basically the bearing, this is the bearing and this is the shaft. Is it okay? So this is the bearing dimension, the whole dimension. That means this is the inside dia, okay, of the bearing. So XH is the whole diameter. Why have we used X? Because you are producing such bearings is large number, so obviously they are considered a random variable. That's why you use this notation XH. So whole diameter inside. And what is the shaft? Shaft also being produced in large numbers. Is it okay? Obviously this is also XH is also a random variable, is also a random variable. So XH is the shaft diameter, that is the outside diameter. And for clearance fit, what is the condition you have to ensure? That is XH, that means inside dia, must be greater than the outside dia of the shaft, that is XS. This is okay. So this is the conditions. And if you consider the distribution of shaft and hole, okay, in hole diameters, is it okay? Hole diameters, the feet, that means in the clearance fit, is it okay? Hole diameters. So so for clearance fit, you have these conditions. Is it okay? So for XS is the random variable, that is the shaft dimensions, and this is the whole dimension. So so the whole dimension should be greater than the shaft dimension. Is it okay? Corresponding shaft dimensions. Now you have this distribution, that means several values you get, and they are assumed to be normal distribution. So you have mu h as the process mean, and you have sigma h as the standard deviation of the whole dimensions, and similarly you have for the shaft dimensions, you have the process mean as mu s and the standard deviation as sigma s. Now you have UNTL, upper natural tolerance limit for S, and lower natural tolerance limit for S. Is it okay? So this is say actually the natural tolerance limit, and similarly for the whole you have UNTL H and LNTL H, subscript H. So the difference between these two, okay, is referred to as natural tolerance limits. Now almost all values of the shaft diameter are less than those of the whole diameter. That means here the shaft dimensions are all lying over here, whereas the whole dimensions are all lying over here. Suppose you are producing 10,000 such the shafts as well as the 10,000 such bearings, okay. So you have 10,000 values over here, you have 10,000 values over here. So this is the distribution. So there is hardly any overlap, there will be no overlap. There is no overlapping, and lower natural tolerance limit for the whole is significantly greater than upper natural tolerance limit of the shaft. Is it okay? So you just refer to this diagram, you keep in mind this diagram or this figure. So everything is made very, very clear. Similarly for the interference fit, it's just the opposite. That means on the left hand side you have the whole dimensions, on the right hand side you have the shaft dimensions. So almost all values of the whole diameter are less than those of the shaft diameter. Is it okay? There could be few in the stray cases, but we ignore. So you are not 100% sure because it's a statistical analysis. That's why I mentioned almost. I cannot say 100% because there could be a stray case, like one point maybe somewhere here, or another point or the dimensions. Okay, one value related to the shaft dimension maybe somewhere here. So that is unavoidable. Those are the stray cases. Those are referred to as the outliers. So just note down the point called outliers. Now here is a systems in any practical system. Okay, you cannot create a system where there will be no outliers. So there is no overlapping, and LNTLS, that means lower natural tolerance limit for the shaft dimension, is substantially greater than upper natural tolerance limit for H. Now for a transition fit, there is overlapping. Is it okay? So this is the distribution with the shaft dimensions, and this is the distributions with the hole dimensions. Obviously this area is the overlap. Is it okay? That means here is a production system. It produces like this. So suppose you opt for interference fit. Interference is desirable one, but what we produce this one? So obviously there will be many transitions. There will be many non-conforming output. So substantial number of assemblies are in overlapping zone. This may be 25% of the cases, or maybe even 50% of the cases. Okay, depending on what sort of the data pattern you have. If there is no control, the proportion of non-conforming can be very high, say 25%, 30%. You are seeking for say transition fit, or say you are seeking for the interference fit, but what do we get? You know, the clearance fit, say 50% of the cases. So those will be the rejections. Both kinds of fit may occur, as I have been pointing out, and this is obviously an undesirable condition. Is it okay? So as far as possible, the transition fit condition you should avoid. So this is your reference. You can opt for this one. Okay, so I conclude this discussion on this.